Hi guys, sound check. Hi again. This is just a sound check.
Hello.
Okay, that's good.
Hello there.
We will start in a second. Okay, so let me explain what I'm going to do today. Well, I want to discuss a polynomial ring in one variable. It has very specific properties, and I want to be focused on them. And the next, well, a bit later, we will discuss polynomials in several variables, but for now, we want to deal with a simpler object. So now I want to discuss polynomials. In one variable. Okay. Oh, just give me 1 second. No, this should be good. Okay, so let me recall. What do I want to call by a polynomial? So I want to discuss polynomials with coefficients in a field. So I want to fix a field. And I want to consider the set of pictures of this form, where all the coefficients are from the given field. And this is basically it. So this picture is a polynomial, and as I already mentioned, the two polynomials are equal if and only if all the coefficients are the same. So if we have a different polynomial, then these two polynomials are equal if and only if for all k, for all natural k, ak is equal to bk. Well, in this case, I assume that if a coefficient is not present here, for example, an plus 1, an plus 2, etc., they're just 0. So if I assume that all the coefficients that are with the index larger than n are 0, then it's fine to use this formula. So this simply means that there is exactly the same amount of coefficients and all the coefficients are the same. And there are just formal rules how to add and multiply polynomials. Let me just recall. So for this sum, you just sum everything the coefficient wise. And if you want to multiply two polynomials, you just multiply them by these rules, ak times am, where k plus m equals d, sum over d, like this. So this is a multiplication in a field. So these are operations in the field f that is given for us. So this is an expression for the coefficient for the power d. And here I use operations from the field, and also this operation sum is also from the field f. And this one is the formal sum for the polynomial. I will denote the set of all polynomials in one variable x with coefficients in f by this. So this is just the set of all polynomials. Let me write it like this, from f. And the set of all polynomials with the operation plus and the multiplication is a commutative ring. And I want to discuss the properties of this ring. Well, first of all, each polynomial produces a function. So let me give you a remark. So if we are given a polynomial f, so this is just a picture, then we may define a function f hat from f to f, which takes each element a to f of a, which is, by definition, is just the sum of this form. So this is a map from the field f to the field f. So if I denote the set of all functions from the field f to the field f as the following, fun, let's name it like this, is just the set of all functions. Let me use a different letter in order to avoid a confusion. Just any function. Then, when we provide a ring structure on this set as follows. If we have two functions, g1 and g2, how to add them together? So the sum of two functions on an element x is defined as g1 of x plus g2 of x. So just the usual sum of functions that we use in calculus. And also we may define the product of functions in a similar way. It's just the product of the results of these functions. So then one may check that the set of all functions is also a commutative ring with respect to these operations. Is a commutative ring just in case, what are the zero and the identity element of this ring? Well, the zero function, which is a function taking each element to the zero element, is the zero element of this ring. And if you take the function which takes each element to the one, a constant function, then this is the identity element of this ring. So this is just another ring, commutative ring. And the procedure described above, which takes each polynomial to a function, f goes to f hat, is an example of a ring homomorphism.
Isn't a polynomial also a function?
Well, by definition, a polynomial is a picture of this form. Let me show you the difference. Well, what I'm saying that, if you think of a polynomial as a picture, then each picture produces a function. But different pictures may give you exactly the same function. So, I mean, it's more convenient to deal with pictures than with functions. For example, if I take f to be z2, and I take f1 to be x and f2 to be x squared, then both polynomials, so these are different polynomials, but both polynomials give you exactly the same function. Because how many elements do you have inside this field? You have only two elements, 0 and 1. And f1 hat function takes 0 to 0 and 1 to 1. And f2 hat takes 0 to 0 and 1 to 1. So the corresponding functions are the same, but the polynomials are different. So this is the reason why I want to distinguish polynomials. I don't want to think of these polynomials as a function, as functions. I just want to think of them as pictures. Is it clear now what I mean?
Yes.
Yes.
And so what did you say above?
Where?
Like where you had like f of a and
Here.
yes.
Okay, what I'm saying here is that this is the set of polynomials. And each polynomial, so each polynomial is a picture, but each polynomial produces a function by this rule. So if I have a polynomial, the formula for the polynomial defines a function. But different polynomials may define exactly the same function. So here is the difference. It's, well, your polynomials may be equal as functions, but they may have different coefficients. So this is not the equality I want to use. I want to compare polynomials just by coefficients. In order to be able to do that, I need to deal with polynomials as with pictures, not as with functions. Because two functions are the same if and only if they have the same value at each point.
Oh, okay, I see. So basically, like f hat is
a function.
Just the function from our polynomial. Okay.
Yeah, exactly. And this rule, which transforms a polynomial to a function, is a ring homomorphism. Well, there are a lot of fancy words, but I mean, what is important is just to understand that for me, polynomials are not functions, they are just pictures. So if I'm saying that two polynomials are the same, I mean that all the coefficients are the same. And I do not test them at each point of the field for equality. Okay, so could you please divide task on the blackboard so it would be more comfortable to read later? Oh, you mean the horizontal lines? Okay, I'll try my best in dividing everything. Oh, okay. So now, okay, so I want to discuss several notions related to polynomials. First of all, the degree of a polynomial. Well, if we have a polynomial in a ring like this, so when I want to say that I'm given a polynomial with coefficients in the field f, I will write something like this. Well, this is just by definition. This means by definition that f is a polynomial with coefficients in f. So just simpler to write this thing than something else. So this is a picture of this form. And suppose that this coefficient is not 0. Then by definition, I will say that the degree of this polynomial is n. So the degree is the largest degree with non-zero of the variable with non-zero coefficient. Well, there is one special case for this definition. What if we do not have at least one summon here? Well, it may happen only in one special case when f is 0. So if we have a 0 polynomial, so the sum is empty. In this case, we just define the degree of the 0 polynomial to be minus infinity. So the degree of a constant non-zero polynomial, let's say the degree of 1, is 0, because then a 0 is non-zero coefficient, so we have x to the 0 in front of a 0, so that's why the degree is 0. But for the 0 constant, we have this special definition. So we will assume that the degree of the 0 polynomial is minus infinity. I will later explain the reason why we are doing that, but this is the definition. And now there is one simple property of the degree. So if we have two polynomials and F is a field, then the degree of the product is the sum of the degrees. And this rule works even in the case when f or g is 0. In this case, we assume that minus infinity plus something is also minus infinity. So that's how to use this formula with this special symbol. But if the polynomials f and g are non-zero, then this is true. And here it is important that f is not an arbitrary ring, but a field. Well, it's actually enough to say that f doesn't have 0 divisors, but I don't want to go to the full generality. And how do we prove this? If we have one polynomial and we have a different one, if we multiply these two polynomials, then you may see that the highest possible degree will be n plus m, and the coefficient here is the product of the leading coefficients of f and g. And if a is non-zero and b is not 0, which means that the degree of f is n and the degree of g is m, then their product is not 0, because in a field we do not have 0 divisors, because f is a field. And that's why n plus m is the highest degree of the product, and we have this formula. But if you take a ring with 0 divisors, this is not true. Well, it may happen that you multiply a polynomial, let's say by itself, and you will get a constant or even 0, as we saw earlier during the previous lecture. So it may happen. Okay, so I defined the ring of polynomials in one variable. Now let's discuss the technique that we may use in order to study this ring. And the main technique that we have is the Euclidean algorithm. We can divide polynomials with remainder. So let me recall what this means. I believe you already know how to divide polynomials with remainder, so I just want to recall all the notation here. So suppose we have two polynomials, and f is a field. So everywhere here, f will be a field. And suppose that g is non-zero. Now I want to divide f by g with a remainder, which means I want to represent f in the form q times g plus r, where q and r are also polynomials, and the degree of r is strictly smaller than the degree of g, the polynomial, the divisor. So in this case, q is a quotient. Let me use a different color. Q is a quotient, and r is a remainder. So this is a remainder. Okay. Now, if the remainder is 0, we just simply say that g divides f. So G divides F. I will use this symbol, or there is a different symbol. F is divisible by G. You may use any symbol you wish. Means that F is represented as Q times G without any remainder. And just in case, we assume that the zero polynomial is divisible by everything. Now this leads to the notion of a greatest common divisor. So let me recall. So if we have two polynomials, then what is the greatest common divisor is a polynomial, is also a polynomial, is GCD of F and G, if it satisfies the following two properties. The property number one, it divides F and G. So it must divide F and it must divide G. And also, this is the largest possible divisor in the following sense. If some polynomial also divides F and G, then this polynomial divides D. So this is the definition of a greatest common divisor. So let me give you one example. So if I have a polynomial like this, x squared plus x and x squared, then the greatest common divisor will be x. However, the greatest common divisor is not uniquely determined. You may multiply the greatest common divisor by any non-zero constant. So if I take an arbitrary element from F star, which is the set of non-zero elements of the field, the set of invertible elements of the field, this is the same, then lambda x is also a greatest common divisor for these two polynomials. So the greatest common divisor is defined up to multiplication by a non-zero constant. So it's not unique. So in order to specify some greatest common divisor for uniqueness, you may require that the leading coefficient of the greatest common divisor to be 1. So if you specify this property, then the greatest common divisor will be uniquely defined. Okay, and let me recall the properties of the greatest common divisor that I want to use. So if we have two polynomials, f and g, from f of x, then first of all, the greatest common divisor always exists. The second, if we have two different greatest common divisors, if d1 and d2 are GCDs of f and g, then one of them is a multiple of the other one, where lambda is a non-zero coefficient, non-zero element of the field f. And what is the most important, there are two polynomials u and v such that suppose, and if d is a GCD, any GCD of f and g, then there are polynomials u and v such that d is represented as a linear combination of f and g, with u and v being its coefficient. So you may represent any greatest common divisor as a sum uf plus vg, where u and v are some polynomial coefficients. Okay, so these are all properties of the greatest common divisor that I want to use. I'm not going to prove this because this is just a waste of time, since the proof is exactly the same as you do in integer for the integers. So the proof is the same as for integers. And here I just want to explain some analogy. So when we deal with integers, we usually take something like the smallest possible positive integer. So we take the module of the number and consider the smallest, let's say, non-zero or some other special integer. In case of polynomials, we need to take the small, well, when we want to, when we want to, how to say, when we want to do the same thing, instead of module, we use the degree. So instead of saying we consider the smallest possible integer, we say we consider the a polynomial with the smallest possible degree. So this is how you adapt the proofs from the world of integers to the world of polynomials. Okay. Now, what I want to explain next. Yeah, and there is an effective way of finding the greatest common divisor using extended Euclidean algorithm. Let me say a couple of words regarding this algorithm. So it's based on the following idea. If we have, let's say, yeah, I'm trying. So if we have two polynomials, f and g, and let's say h is another polynomial here, then the greatest common divisor of f and g is exactly the same as the greatest common divisor of f and g minus hf. So this is one of the property that I want to that I would like to explain. And using this property, we can efficiently compute the greatest common divisor for for every pair of polynomials.
Excuse me, may I ask a question?
Yep.
Do I understand correctly? Like h is also a polynomial from ring
yep.
f? Okay.
Yep, it's written here. Yep.
All right.
Yeah, so if you have two polynomials, f and g and h, well, actually, if we have three polynomials, f, g, and h, then we have this property that the greatest common divisor for f and g is exactly the same as the greatest common divisor for these new pair of polynomials. Well, you already know exactly the same rule for integers. So when you use extended Euclidean algorithm to compute GCD, you use the same property. So first of all, let me explain how to prove this, why this property holds. So let's see. Well, I want to denote the left-hand side by D1 and the right-hand side by D2. So in order to show this equality, well, again, by definition, what is a GCD? Well, it's a divisor. So, well, if we want to prove that D1 equals D2, we need to check all the properties. Well, again, D1 and D2, they are not uniquely determined, but let's assume that they have leading coefficient to be 1, then we can prove that they're the same. So what is D1? D1 must divide F and G, and if something divides F and G, then it divides D1. So these are properties for D1. What are the properties for D2? Well, D2 must divide F, and D2 must divide G minus HF. And the second property, if something divides F and divides G minus F HF, then H divides D2. So I want to show you that these, well, if D1 satisfies these properties, then D1 satisfies the other ones, and vice versa. If D2 satisfies these properties, then D2 satisfies this one. Then we will show that the set of greatest common divisors for this pair is exactly the same as the set of greatest common divisors for this pair. Okay, so.
Excuse me.
Yep.
Just a small question.
Yep.
Is the H on the right side the same for the one?
I see. That's my mistake. That's my bad. Let me denote by a different letter. Let's say what kind of letter did I use? Let's say T. Not the best choice for the name of a polynomial, but yeah, thank you very much. That was a mistake. So for every polynomial T dividing these polynomials, T must divide D2. Well, roughly speaking, what this means? Well, okay, so let me explain the idea of what's going to happen now. So I want to consider all divisors of F and G, and this will be one set. Then another set will be the set of all divisors of this pair. If these two sets are the same, then the greatest elements of these sets with respect to division are also the same. So then the greatest common divisors are the same. This is what I want to explain. So now, suppose that we have a polynomial dividing F and G. So these properties hold. Then I'm saying that these properties also hold for D1. Indeed, this one is exactly this one. But if D1 divides F and G, then it divides this difference because all summands are divisible by D1. So if D1 divides F and G, then D1 divides F and G minus HF. In a similar way, if we have a polynomial dividing the right hand, dividing F and G minus HF, then it divides F. Well, first of all, it divides F, and also it divides this guy plus HF. So it must divide G. So the set of divisors for this pair is exactly the same as the set of divisors for the other pair. So the set of divisors of FG is exactly the same as the set of divisors of this pair. But what is but what is the greatest common divisor? Is an element for FG, is an element of this set which is divisible by everything else from this set. What is the greatest common divisor for these two polynomials? Is an element of this set divisible by every other element of this set. So these are exactly the same notions. So every yep.
Can you elaborate a little bit again on why is the set of divisors for the left-hand side is the same as the set of divisors for the right-hand side?
Okay. Let me repeat. Suppose that we have something. Let's say we have a polynomial. Let's say P, and P divides F, and P divides G. Then what does it mean? It means that F is equal to P times F0, and G equals P times G0. Then, if I consider G minus HF, this is equal to P times G0 minus HF0. So this simply means that, yeah.
I see. Thank you.
P divides this difference. So, so this proves this inclusion. If you want to prove the opposite one, then you denote this polynomial by G prime. Then the polynomial G is of the form G prime plus HF. So the argument is exactly the same when you need to prove the inclusion in the other direction. So now, since the set of divisors for each pair is the same, then then the greatest common divisors in both sets are the same, just by definition. So that's why the set of greatest common divisors for this pair is exactly the same as the set of greatest common divisors for this pair. Are there any questions regarding what was going on here? Probably it wasn't really okay, but I hope at least I was able to clarify what I wanted to explain.
Yeah, I think it's okay.
Okay, so now what is the idea of finding the greatest common divisor for two polynomials? So if you want to, how to find a GCD. So if we're given two polynomials, f and g. So what you can, well, if one of them is 0, then just by definition, first of all, if you a GCD of f and 0 is just by definition is f. Well, if you go to the definition and like think for a couple of seconds, you will see that, well, f is the polynomial satisfying the definition, because what what is the set of all divisors for f and 0? Well, 0 is divisible by everything, so the set of all common divisors for f and 0 is just the set of all divisors for f. So so what is the greatest divisor? Is the greatest divisor among all divisors for f, but then this is f. Well, strictly speaking, I should write lambda times f, where lambda is a non-zero coefficient, because the set of greatest common divisors, well, this is a set. I mean, the greatest common divisor is not uniquely defined, but writing this, well, I'm just abusing notation. I mean that every polynomial proportional to f is the greatest common divisor, but I hope that's okay if I use this form. So now, if I want to find a GCD of this pair, I just want to reduce one of these polynomials to 0. How do I do this? I divide f with the remainder by g, and then, as I can see, r is represented as f minus qg. So the greatest common divisor for g and f is exactly the same as the greatest common divisor for g and r. This is because of the previous formula. Now I can repeat the process. I can divide g with remainder and replace this by the next pair, and so on. Now, what happens during this process? By the definition, the degree of the remainder r is strictly smaller than the degree of g. That's just by definition. Then, when we look at the second equality, the degree of the remainder r1 is strictly smaller than the degree of r, because r is the divisor. So, when we repeat this process, the degree of the second polynomial here always strictly decreases. But since the degree is a natural number, this process cannot go infinitely long. So after several steps, the second polynomial will become 0. So after several steps of this process, we will find that the second polynomial is 0. Oh, I forgot to write GCD. So the answer will be the last non-zero remainder. So if you want to find the last non-zero remainder, or if if you compute the last non-zero remainder, this will be the GCD for the initial pair. So this is how you find a GCD in the general case. Okay. You can also adapt this algorithm to find the expression of GCD as a linear combination of the initial polynomials. But we'll discuss this algorithm during the seminar session. So you can, well, there is a version, there is a way to expand this GCD as a linear form like this, where U and V are some polynomials. So everything here is very similar to what we did with integers. So I just don't want to be very precise with all the claims. Okay, are there any questions regarding this algorithm? Okay. Okay. So let's move on. This is just a technique. So now, what can we do using these algorithm? Well, actually, all the properties of the polynomial ring directly follow from the existence of these division algorithm. And all the properties will be very similar to the ones we have with the usual integers. So what kind of properties do we have? Well, first of all, the claim number one. Let's discuss let's discuss the ideals of this polynomial ring. So suppose F is a field and I is an ideal of this polynomial ring. Then there exists a polynomial such that I is of the form F times H, where H goes through all the polynomials here, and the name for this set is F in parentheses. So every polynomial, every ideal in this ring consists of polynomials divisible by a fixed polynomial F. So for every ideal, we can find a specific polynomial F such that all elements of this ideal are just multiples of this polynomial. So let me explain how the proof works. So why it's true. So the proof here is exactly this. So first of all, the claim is exactly the same as the claim for the integers. We know that in the ring of integers, every ideal is the set of all integers divisible by a fixed integer. So first of all, there are two cases. The case number one, the ideal contains only the zero polynomial, and the case number two, there is a non-zero polynomial inside I. Well, if we have the case number one, then we can take F to be zero, and then clear that 0 times everything is just the 0. Now, so now we may switch to the second case. In this case, first of all, we need to find this specific polynomial F defining our ideal I. How can we find such a polynomial? Well, let's take a non-zero polynomial of I with the smallest possible degree. So since we have at least one non-zero polynomial, we can find F in I such that F is not 0, and second, the degree of F is the smallest possible. And now let's prove that every polynomial in I is divisible by F. So let's take an arbitrary polynomial G of I and divide it by F with remainder. then G is represented as Q times F plus R, and just by definition, the degree of R is strictly smaller than the degree of F. And we can rewrite this as G minus QF. And by definition of the ideal, what do we have here? G was from the ideal, that's because of this. G was taken from the ideal. Now, F is from the ideal because of the definition of F. It was taken from the ideal. Now, since Q was an arbitrary polynomial, if we multiply Q by a polynomial from the ideal I, then this product is also in the ideal I, just by the definition of the ideal. And the difference is also inside the ideal. So we can see that R is inside the ideal I. But now we see that the degree of R is strictly smaller than the degree of F. But F was the smallest, was a non-zero polynomial with the smallest possible degree. So since R is also inside I and has strictly smaller degree, there is only one option. R must be 0. By the choice of F, R must be 0. So this means that G is divisible by F. So now we know the description of all the ideals in this ring. So every ideal is of this form.
Sorry, can you please recall the definition of an ideal?
Oh, okay. Give me a second. So the remainder, not the remainder. So a subset of a ring R is an ideal if it satisfies two properties. First of all, it must be additive subgroup. So if you forget about multiplication, so this is a subgroup. Well, simply this means that I contains 0. For every element, it contains minus this element. And for every 2 elements, it contains the sum of these 2 elements. And the second, for each element of the ring and for each element of the ideal, the product R times X is in the ideal, and the product X times R is in the ideal. So if you multiply anything from the ideal by anything from the ring, you will get something inside the ideal. So this was the definition.
Okay, thank you.
No problem. Okay.
One question. Could you please explain again why Q is from ideal? Yeah. We have G and F, they're from ideals.
Okay, yeah. You see, F is from ideal. If you Q was a polynomial.
Okay.
If you multiply something from ideal by something from your ring, you will stay inside. Yeah, by definition. Okay. And then if you have something from ideal and you subtract something from ideal, you're also inside the ideal because it's abelian subgroup.
Okay, thank you.
Mm-hmm. Are there any other questions? And as you can see, the proof is exactly the same as the proof was for abelian groups when we described all the subgroups of Z. So the method is exactly the same, as the reason why the proof works is because here we also have this procedure to divide with a remainder. So if you have a problem about polynomials in one variable and you don't know how to solve this problem, just use the division with remainder. Like 99%, it will help you. There is 99% chance that using the Euclidean algorithm will solve any problem regarding the polynomials in one variable. Okay, now I want to discuss the UFD property. So what is a UFD property? I want to give the definition. So first of all, UFD stands for unique factorization domain. It means that if you have a polynomial, you can factorize it's uniquely in a product of like somehow prime polynomials. So I just want to explain all. So with integers, you can factorize each integer into a product of prime integers. So here we have some analogous statement saying that, well, first of all, there is some analogy for prime numbers, which is irreducible polynomials, and then you can factorize each polynomial into a product of irreducible polynomials, and this factorization is unique up to some up to something. So let me explain all these words. So first of all, definition. If we have, well, let's say f is a field, as always, and suppose f is a polynomial from of non-zero degree, of degree strictly larger than 0, I would say. So it's not non-constant polynomial. We will say that this polynomial is reducible if there exist polynomials h and g, non-constant polynomials h and g, such that f is a product of h and g. So a polynomial is reducible if you can factorize this polynomial as a product of non-constant polynomials. And it's called irreducible if there is no such factorization. So f, a non-constant polynomial. So if you are given a constant polynomial, which is an element of f, this term is not applicable. You cannot say it's reducible or irreducible. It doesn't make sense. So reducible or irreducible makes sense only for non-constant polynomials. So for polynomials of degree of positive degree. So we say that this polynomial is irreducible. Well, if, well, for any non-constant, well, let me formulate it like that. If for any polynomials f and g, if f is equal to h times g, then either h is constant or g is constant. H is an f or g is an f. So you cannot represent it as a product of two non-constant polynomials. Okay. Now, another definition. If we have a polynomial of this form, so with the leading coefficient being 1, then we will say that f is monic. So monic means that the leading coefficient is 1. Okay, so it's just very convenient to use monic polynomials when we want to discuss uniqueness or something. So now examples. You probably are aware of all of these examples, but well, the set of irreducible polynomials depends on the choice of your field. So if I take field to be the field of complex numbers, then here all irreducible polynomials, well, monic irreducible polynomials are just linear ones. Reducible means linear. So the monic irreducible polynomials are all of these forms. There are no other irreducible polynomials. If you take your field to be R, so there are two types of irreducible polynomials. You either have a linear, well, monic irreducible polynomials. You either have a linear polynomial, or you take a quadratic polynomial with no roots, which means a square minus 4b is strictly smaller than 0. So these are all irreducible polynomials for R of x. And if you take something like Q of x, then there are a lot of different irreducible polynomials. Well, it's even hard to describe all of them. So in case of Q of x, well, but what is important in this case, for each integer, for each natural, you have an irreducible polynomial. For each natural n, you have an irreducible polynomial of degree n. For example, if you take x to the n minus 5, where 5 is a prime number, then one can show it's not hard, but it's not immediate, but one can show that all these polynomials for each n are irreducible. These are not all the irreducible polynomials of Q of x, but this is an example of an irreducible polynomial of an arbitrary degree of rational numbers. So, okay. And so let me summarize what I have already told you. So here for, well, a remark. Let me write down all polynomials like this. So these are all polynomials with coefficients in the field. So here we have constant polynomials, which is f. And inside f, we have this special polynomial, which is 0 with the degree minus 1 or minus infinity. All the other constants have the degree 0. So then these are just invertible, so non-zero constant polynomials are just invertible polynomials. So these are non-constant polynomials are just non-invertible polynomials. So this set without 0 is f star. This is the set of invertible polynomials. And this set, and this the blue set is precisely the set of polynomials of degree 0, and the yellow set is the set of polynomials of degree strictly larger than 0, and this is the set of all non-invertible polynomials, all non-invertible. Now we divided the set of all non-invertible polynomials in two pieces. So there are irreducible ones and reducible ones. So these are different types of polynomials in a polynomial ring. So you cannot factorize irreducible polynomials, but you can factorize reducible ones. And there is a result saying that every reducible polynomial, which is a polynomial of positive degree, can be uniquely well, you can factorize each reducible polynomial uniquely into a product of irreducible ones. So this is the claim. Well, this claim means that this ring is a unique factorization domain. So you can factorize uniquely each polynomial. So let me write this claim down. So the UFD claim, it says that if f is a field, then every polynomial, every non-constant polynomial is uniquely presented in the following form. F is equal A times P1 to the K1 times etc. and so on, K PS times KS, where A is a non-zero constant, P1 and PS are different monic irreducible. and K1, Ks are positive integers. So this is the analogy for the claim that we know for integers. So every integer number can be presented as a product of prime numbers and probably plus minus the sign plus minus. So A stands for, so the analogy of A is the sign. So for integers, if it's positive, then you have 1. If it's negative, you have -1. And then P1, Ps are just prime numbers, and K1, Ks are just the powers of the prime numbers. And here, in case of the polynomials, well, we have a lot of invertible polynomials which are non-zero constants, so we have more options here. But here we have exactly the same situation as with integers. So this is the Ufd property for the ring of polynomials with coefficients in a field and in one variable. Okay. Well, the proof actually uses the fact that, well, it's long, it's not complicated, but it's long, and the proof is exactly the same as the proof for the integers. And the main ingredient is that greatest common divisor for two polynomials can be presented as a linear combination of these polynomials with polynomial coefficients. So the property number 3 from one of the claims above. So I don't want to repeat this claim, but I just want to show you one specific situation where you can, how you can, well, demonstrating the idea appearing during the proof of the previous claim. So let me formulate something like this. Claim, so if we have two polynomials, well, suppose F is a field, and we have 3 polynomials, F, G, and H, and suppose that GCD, well, let me denote GCD by these braces. So this is just GC by parentheses. I just don't want to write GCD. I just want to use the same notation as for integers. So if they are co-prime, which means that the GCD is 1, and suppose that F divides H and G divides H, then the product also divides H. Let me show you how to prove something like that using the properties of GCD. So this is how the proof goes. When you see a statement like this, that you are given a GCD of a pair of polynomials, then immediately use the property that there are some polynomials U and V, that one can be represented as U times F plus V times G. This is a starting point for any proof using a GCD. You just expand this GCD as this linear combination. Now, multiply this equality by H on the left and on the right, you will get that H is equal to UFH plus VGH. And now I want to prove that this is divisible by F times G. Now, you see here, this is F, but by this property, this is divisible by G. That is, this one is represented as G times H0. From the other, for the other summand, here is your G, but this guy is divisible by F. So by definition, it's represented as F times some H1. And as you can see, the first summand and the second summand is represented as F times G times something. So the result is F times G times UH0 plus VH1. So it's also, so the right-hand side is divisible by the product, and the left-hand side is H. So we're done. So this is how it's done. Okay. So now we are ready to discuss more interesting concept. So in case of integers, how did we use the Euclidean algorithm? We actually had the set of remainders modular some integer, and we provide a structure of a commutative ring on the set of remainders. I want to do exactly the same in case of the ring of polynomials in one variable. I want to define the ring of remainder, the polynomial ring of remainders. So suppose F is a field and we fix a non-zero polynomial here. Well, actually, it doesn't matter, just any polynomial here. Now I want to define the ring of remainders. This will be a notation. This is what I want to define. The ring of remainders. And I want to define it for every polynomial f. So in order to define, well, actually there is a different name for this guy. It's called a quotient ring. Quotient ring. That's just a different name. Okay. The full name, the ring of remainders with respect to polynomial f. So with respect to polynomial f. So in order to define a ring, as you remember, I need to specify 3 pieces of information. The first thing, I need to specify the set. So I need to define the S set. So what are the things that live here? Then I need to provide 2 operations, the addition and the multiplication. And after that, I need to check that all the properties of a ring are satisfied. So let me start giving the definition by specifying the set and then the 2 operations. But before doing that, there is a special case. Well, the definition is given in 2 steps. First of all, if f is a 0 polynomial, then just by definition, we will define this ring of remainders to be just the set of polynomials. So this is just by definition. So now I may assume that f is a non-zero polynomial. So this, for 0 polynomial, this is just the trivial definition. It's not interesting. So now I want to give you the interesting part. So when f is a non-zero polynomial. So now I want to specify the set. So the set is just the set of polynomials in f of x of degree strictly smaller than the degree of f. So this is the set. And as you can see, if you take a remainder of something, when you divide by f, the remainder always be of degree strictly smaller than the degree of f. So this is why you think of this set as the set of all remainders with respect to f. So now I want to provide 2 operations here, an addition and multiplication. So if we have, let's say, G1, so what is an element here? It's a polynomial of this form. If n is the degree of f, then an arbitrary element here is of this form, and G2 must be something like this. So here I assume that n is just the degree of f. Well, now if you add these 2 polynomials together, G1 plus G2, you see that the degree of the sum is strictly smaller than the degree of f, which is n. So the usual addition gives you addition on this set. So the addition is just simply the addition of polynomials. Now, what about multiplication? Well, if you take just the product of these two polynomials, then the degree need not be smaller than n. It actually can be larger than the degree of f. So in order to make the product well defined, you take multiplication modular f. What does it mean? Well, you multiply g1 by g2 and then divide by f with a remainder. Then you say, just by definition, that R is the product of G1 and G2 in this ring. So this is how to define the operation. You take two remainders, you multiply them, then you take the remainder with respect to f, and this is your result. And just by definition, this procedure is well defined because R has the degree strictly smaller than the degree of f. So this is your multiplication. Now, well, there is a claim saying that the set of all remainders with the addition and multiplication above is a commutative ring. Well, we actually need to check all the properties, but you see, I just don't want to do this. I want to specify some, well, let me specify the zero and the neutral element here. So this is without proof. But we will check the properties during the seminar. So I just don't want to prove this. But just believe me, this will be a commutative ring. The most interesting part is that all the operations here are well defined and all the properties are satisfied. So it's just a very boring computation that everyone can do. But it's very okay. So now, what is the zero element here? So the zero element is the zero polynomial. Zero is the zero polynomial. Which is the polynomial with all coefficients being zero. Then what is the identity element? The identity element is the polynomial f, which is 1 plus 0 times x plus etc. 0 times x to the n minus 1. So just 1 from the field. Okay. Now, another important remark, remark number 2, well, by definition, this set belongs to this one. So we just consider polynomials of degree strictly smaller than the degree of f. But the left-hand side is not a subring in the right-hand side. So if I add addition, then f of x modular f with addition is an abelian subgroup here, is a subgroup. But if you add multiplication, then the left-hand side is not a subring. So this thing with multiplication, well, is not a subring of the polynomial ring. This simply means that, well, this is a subset here, and the operation plus is exactly the same as here, but the multiplication is completely different. So it's not true that this is a subring here. That's a very important remark, because multiplication here is just the usual multiplication, and multiplication here is multiplication followed by this taking remainder operation. Okay. Now, are there any questions regarding this object? So let me summarize what was going on here. I have just defined a ring, which is a set, and two operations, addition and multiplication on this set. And the claim is that this guy is a ring. Okay. So since there are no questions,
I'd like to ask a question, please.
Okay.
About the notation. So you write f of x slash f. What does the slash f part mean?
Okay. There is a notion of a quotient ring. If you are given a ring and an ideal, you can produce a quotient ring. There is a notion of a quotient group also, but I use the notation of the quotient ring, but I just don't want to give you the general procedure how to produce a quotient ring. So this well.
So
okay,
this is just a quotient ring of an ideal f.
Yep, exactly.
Okay.
So if you know what is a quotient ring by an ideal generated by f, this is it. Yes, precisely. I just don't want to use all these words.
Thank you.
No problem. Okay, so now I want to formulate a Chinese remainder theorem for the remainder ring of polynomials. So the Chinese remainder theorem. So suppose f is a field, and we have two polynomials here in f of x. Okay, and suppose that these two polynomials are co-prime, so their GCD is 1. Then we have a map. Let me write this down like this. So I want to write this down, and then I will clarify all the details here. So you see here we have three different rings. So first of all, the ring of remainders modular f times g, the ring of remainders modular f, and the ring of remainders modular g. And here we take the direct product of these two rings. So this is the ring of pairs, like this. And I define a map which takes a remainder here, which is a polynomial h of degree strictly smaller than the degree of this product. And I map this polynomial to a pair h modular f, which is the remainder of h with respect to f, and h modular g, which is a remainder of h with respect to g. So the claim is that this map is an isomorphism of rings. So the claim is very similar to the one we had for the integers. So this is somehow the analogy of the ring of remainders for the integers, but we produce the same ring with, well, a similar ring with polynomials. Okay, are there any questions regarding the statement of the claim? Okay, so let me show you how to prove this. So first of all, in order to prove this, we need to prove several things. The thing number one, this map is a homomorphism. So it preserves addition, multiplication, and the identity element. The second claim, we need to show that this map is bijective. So let me start with explaining why this map is a homomorphism. So first of all, we need that phi preserves the addition, multiplication, and the identity element. Well, this is just a straightforward computation because you see, when you take h to this pair of remainders with respect to f and g, then this rule is compatible with addition and multiplication modular f times g. Well, this immediately follows from the definition of the operations. And if you take the element 1, then element 1 goes to 1 modular f, 1 modular g, which is 1, 1. So this is just by definition. So it's just a straightforward computation. Okay. Now, well, so I don't want to be more precise here. I hope. Well, this is a good mental exercise, so try doing this. But let me switch to the second part. I just want to explain why this map is an isomorphism. And in order to show that this map is an isomorphism, we need to show that it's injective and surjective. And I'll show the injectivity first, and then I'll show how to prove that the map is surjective. Well, first of all, injectivity is injective. Well, in order to show that phi is injective, we need to show that the kernel of phi is 0. Since we already know that phi is a homomorphism, it's sufficient to compute the kernel of phi. But what is the kernel of phi? The set of polynomials here such that phi of h is 0. But what does it mean that phi of h is 0? It means that, well, phi of h by definition was the remainder of h with respect to f and the remainder of h with respect to g. So what does it mean it's 0? It means that f divides h and g divides h. So this is 0 if and only if these two conditions hold. But as I already proved, as I already shown you that, well, if you have a pair of polynomials, f and g are coprime, then the product must divide h. That was the previous claim. So, but then, by definition, a polynomial here is of degree strictly smaller than the degree of f times g. So the only option here, so since the degree of h is strictly smaller than the degree of the product, the only option here is that h is 0. So that's why, so that's why the kernel consists of the 0 polynomial only, and the map phi is injective. So that's how you check that a map is injective. Yeah, I see that I have -3 minutes. I just need like 2 or 3 minutes more and I will be done. Just in case, are there any questions regarding this part? Okay, then now how to check that the map is surjective? Well, here we will use the linear algebra. Well, in order to check that phi is surjective, we will use the linear algebra. For doing that, well, you see, we know that phi is injective map from this ring to this one. So in order to show that it's surjective, we need to check that well, we will consider the left-hand side and the right-hand side. as a vector space over F. So my claim is that this guy and this guy, they are vector spaces over F. And phi is a linear map. So if I show that the dimension of the left-hand side coincides with the dimension of the right-hand side, then we're done. Because of injectivity, the image must have the same dimension as the source. But what is the dimension of this guy? Well, what is this one? By definition, it consists of all polynomials of degree strictly smaller than, well, let's say the degree of f is n and the degree of g is m. Then this guy consists of all polynomials of degree strictly smaller than the product. So there are m times n linearly independent monomials. So the dimension of this guy is n times m. Okay, so in a similar way, the dimension of this guy is the degree of f, and the dimension of this guy is the degree of g. So all these things are finite dimensional vector spaces over f. And when you take a direct product, then what is the basis of the left summon? These are powers of x from the 0 to n minus 1. What is the basis of the right hand side? Well, of the second factor. These are powers of x from 0 to m minus 1. So what is the basis of the direct sum? Well, one can show that the elements of this form is the basis of the direct sum, because the direct of the direct product, because, well, the direct product is basically the direct sum of the vector spaces. So this is the basis. Oh, I'm sorry, I'm doing it wrong. Oh no. What I did wrong here, the degree of f times g is not m plus n, is not m times n, is m plus n. That was my bad. So okay, so let me go again. So when I want to compute the dimension of this guy, well, by definition, here I have polynomials of degree strictly smaller than f. So the monomials 1, x, x squared, etc., x to the power of degree f minus 1 is they form the basis of this vector space. So how many do we have here? Well, exactly the degree of f. So the dimension of these is the degree of f, the dimension of this is the degree of f, and the dimension of this is the degree of f times g, which is the degree of f plus the degree of g. So that was a mistake here. So here must be the sum of these two integers. And since here the basis of this space is just the union of the bases, like here, the dimension of this space is also m plus n. And as you can see, the left-hand side and the right-hand side, they both have the same dimension, and the map is injective, so it's automatically surjective. So the dimension here is also m plus n, and we're done. Okay, I'm sorry for being so late, but I'll try to write the proof with more details in the lecture notes. So I hope it's not so critical if it wasn't really clear during the lecture. But just in case, are there any questions here?
Well, it depends on whether you're ready to elaborate on some bits that you described previously during this lecture.
Okay, but go on. I have time.
Can you like make it smaller so I could pinpoint the precise location?
Okay. Oh, yeah. The form of the notes is really strange.
I guess from this place where you have red text
Here.
on the right here. Yeah, this one.
Okay.
Yes, like from the second point, can you explain what is happening?
Oh, okay. So you see, by definition, this guy as a set was a subset here. So it's a sub. So let me add this is a subset. Okay. Because
but what kind of subset is it? I don't really get by the description.
Okay, so what was this by definition? If f is 0, then this is just the set of all polynomials. If f is not 0, this is just the set of polynomials of degree strictly smaller than f. So here is the definition. So by definition, this guy consists of some polynomials from here. So it lies inside the set of all polynomials. So it's a subset there.
I see.
Okay, so it's a subset. Then, if you take a look at the operation, at the addition, actually, then the addition was defined as the usual addition of polynomials. So this subset here becomes a subgroup with respect to addition. So, okay, so it's a subgroup. But then there is a second operation, which is multiplication. And here is the difference, the crucial difference between this guy and this guy. So here the operation is multiplication following by taking the remainder. And the operation here is just usual multiplication of polynomials. So the multiplication is completely different here and here. So this is a subgroup with respect to addition inside the set of in the group of polynomials, but it's not a subring. So the multiplication, well, I mean, this inclusion doesn't respect multiplication. If you take two elements here and multiply, the result will be different when you consider these elements as just arbitrary polynomials and multiply here. So that was the point here.
I see.
That's just okay. Are there any other questions?
If you can you like describe this claim?
Oh, the claim again. Okay. Well, this is the Chinese remainder theorem for this ring of remainders. So you suppose you have two polynomials with the coefficients in a field, and these two polynomials are co-prime. So the situation is very similar to the situation with integers. You have two integers and they're co-prime. Then you can produce the two rings. On the left-hand side, you take the remainders with respect to the product of the polynomials. So that was very similar to the integers where you take z mn, the remainders with respect to the product. And on the right-hand side, you take the remainders with respect to one polynomial with respect to the other polynomial, and then you take the direct product of these rings. So just the pairs from here and here. And this is also a ring, a commutative ring. And now you have a map between these two rings. You take an element here, which is a polynomial of degree strictly smaller than the degree of the product, and you take this polynomial h to its remainder with respect to f. So you just divide h by f with the remainder and put here the remainder. and then you divide h by g with the remainder and put here the remainder. So this is the map from the left-hand side to the right-hand side. And now the claim says that this map is an isomorphism of rings, which means that phi is a homomorphism, so it preserves the addition, multiplication, and the identity element. And also it's bijective. So this is what claim states.
I see.
So I skipped the part explaining that this map is a homomorphism because it's just a straightforward computation. And then I was trying to explain why phi is injective and why phi is surjective. So you can check directly the injectivity using the kernel. And then you have a trick to show the surjectivity using the fact that these two rings are actually finite dimensional vector spaces, and you can compute their dimensions.
Yes. Yeah, I remember this.
Okay. Are there any other questions?
I guess not. Thank you for elaborating on this piece of lecture again.
No problem.
Yeah, I have one question. Could you show us the definition of GCD again?
The definition of the GCD?
Yeah.
Okay. Here it is. So a GCD is any polynomial satisfying these two properties. So you have like infinitely many GCDs for every pair of polynomials.
So
But,
by definition, it's not unique.
Yeah, by definition, it's not unique because you can multiply every GCD by a non-zero constant and will also satisfy these two properties.
Okay. Okay, and what is UFD?
UFD is the property of the ring. UFD means unique factorization domain. Yeah, let me go here. So I'm saying, saying that f of x is a unique factorization domain means that this claim holds.
Okay, got it.
So the statement of this claim means that the polynomial ring in one variable with coefficients in a field is a unique factorization domain. So roughly speaking, you have a unique decomposition into a product of primes. Well, here irreducible ones. Monic irreducible.
Okay, thank you. And the last question,
Okay.
On the diagram above, you said that if that polynomial is invertible, its degree is 0.
Yep.
Why can't we find a polynomial with degree greater than 0, but still be invertible?
Okay, because for the polynomials with the coefficients in a field, if you multiply two polynomials, the degree of the product is the sum of the degrees. So if you want f times g to be 1, 1 is the polynomial of degree 0. So the degree of f times g must be 0.
Okay.
So the only option here is that the degree of both polynomials is 0.
And we don't have negative degrees.
No, we do not have negative degrees. Well,
so they're invertible.
Yeah.
They are invertible. It must be, the degree must be 0 when you are talking about inverse in relation to multiplication, right?
Yeah, exactly. Yeah, and here I use the fact that the coefficients belong to a field. If you take a different ring, which is not a field, it may happen that a polynomial with positive degree is invertible. It may happen. But if your coefficients belong to a field, then only non-zero constant polynomials are invertible. Yeah, in 1 minute we need to start the seminar. Or probably in 2 minutes or in 10 minutes. I just forgot.
10 minutes.
In 10 minutes. Oh, we have like 10 minutes more. Then if you have any other questions, then just ask. I'll try to answer. Or I can explain if something was vague or unclear. Oh, but this lecture probably wasn't the perfect one, I think. Okay, any other questions? Okay, guys, since there are no questions, then I think see you in a week or in 10 minutes, depending on whether you're from the first group or not. Yeah, thanks for being here.
Thank you. Thanks for explaining everything twice.
No problem. That's why I'm here. Because you see, education doesn't mean that I'm saying something once. Education means I'm explaining everything that you can understand this. So,
Well,
yeah,
thanks.
no problem.